Hello and welcome. Today, we delve into a story that reveals a hidden truth about World War II armor, one that challenges everything you thought you knew. Imagine a single, fully operational American Sherman tank captured in North Africa, still running after a grueling 350-kilometer trek across hostile terrain, its engine cool and transmission flawless. How could this be possible when German tanks, renowned for their engineering, often broke down after just a few dozen kilometers? What secret did this tank hold that shook the very confidence of German engineers and military planners? Could it be that American industry had unlocked a form of engineering mastery that the Germans had not yet grasped? And what does this tell us about the real strength behind the Allied victory, firepower or reliability? From the remarkable endurance of War Daddy II to the strategic trials at the Kummersdorf Proving Grounds, these facts form a pattern. American tanks were built not just for performance, but for relentless, dependable operation. How did they achieve such durability? Why did the Germans, despite their scientific prowess, struggle to match this reliability? And what lessons did the Germans learn, too late, that mass production and practical engineering could outmatch even the most advanced technology? The central question then arises: is technological sophistication enough if your vehicles cannot reliably reach the battlefield? The answer, proven repeatedly in the trenches and testing grounds, points to one undeniable truth: reliability is victory. And as we uncover the layers behind this technological gap, one thing is clear. The true weapon of the Allies was not just their firepower, but their industrial capacity to produce tanks that simply would not fail. So, join us as we trace the journey of War Daddy II from capture to testing, revealing the profound difference between German precision and American pragmatism, and difference that decided the fate of armored warfare in the Second World War. The most important battles start right now. In mid-February of 1943, amidst the rugged landscapes of Tunisia, a remarkable event unfolded that would leave a lasting mark on warfare technology. A lone M4A1 Sherman tank, a symbol of American industrial might, brought to a halt in the arid desert sands. Its distinctive American star was still visible beneath the hastily added camouflage of a German cross, a stark reminder of the fierce battle that had just taken place. A group of German officers from the Heavy Panzer Battalion 501 quickly gathered around this unexpected prize, their notebooks open and poised to record every detail of the encounter. This singular capture, an American Sherman tank that remained fully intact and operational during the Battle of Sidboid, would prove to be a seismic event for the German war effort. It did not merely represent a tactical victory but also sparked a profound crisis of confidence among German engineers and military planners. What it revealed about American tank philosophy and manufacturing would resonate throughout their armored vehicle development for the entire duration of the war. Here, the emphasis was no longer solely on firepower or armor plating. Instead, the focus shifted toward something that the Germans had not traditionally valued: automotive reliability and engineering excellence that refused to falter under the harshest conditions. The tank was famously dubbed War Daddy II, a name painted boldly on its hull. Its serial number, USA 3,067,641, identified it as a product of the Limer Locomotive Works, and it belonged to Company G of the 1st Armored Regiment, which was part of the 1st Armored Division of the United States Army. The German reconnaissance unit that seized the tank then drove it across an arduous 350-kilometer journey through North African terrain, an expedition that took approximately 4.5 days, ultimately bringing it to the port of Espifax. Each kilometer of that trek challenged and defied German assumptions about American industrial capability. The engine remained cool under pressure, The transmission showed no signs of failure, and the final drives maintained their performance steadily without faltering. This relentless reliability was particularly unsettling to German tank crews, who were accustomed to frequent mechanical breakdowns during short movements and extensive reconnaissance missions. As they watched War Daddy II traverse the rugged terrain and unpredictable conditions without a single hiccup, their unease grew. To them, this tank exemplified a level of automotive technology that their own equipment simply could not match or sustain under similar hardships. When the Sherman was finally loaded onto a cargo ship at the port for transportation to Germany, the implications were clear. This was more than just a battlefield trophy. It was a stark demonstration of American engineering prowess. The orders from the German Army's weapons office were explicit. The tank, designated at the time as Zugfahrts 259 and bearing the license plate WH058941, was to reach the testing facility at Kummersdorf completely intact and fully operational. Although German intelligence had received fragmented reports about American tank production, it was the physical presence of War Daddy II that truly brought the realities of American industrial capacity into sharp focus. Visual evidence that numbers and reports alone could never fully convey. This Sherman was a product of mass production on a scale that Germany, despite its formidable wartime industry, was unable to emulate. It was constructed with a level of automotive engineering that the Germans had rarely, if ever, mastered. The significance of this technological disparity was amplified during the voyage across the Mediterranean, where German engineers anxiously prepared testing protocols, rigorous procedures designed to uncover the full extent of their own limitations in comparison to American innovation. By the spring of 1943, at the Kummersdorf Proving Grounds near Berlin, War Daddy II was finally unloaded from its transport railcar, stamped with the designation Zugfahrts 259 and bearing the German license plate WH058941. Every surface of this captured tank had already been meticulously measured. The engineers had marked armor thickness and angles with precise notations, preparing for an exhaustive evaluation that would test the very limits of their understanding. Set within the heart of the German military's primary testing facilities, the Kummersdorf Proving Grounds, located just 25 kilometers south of Berlin, became the arena where the true scope of technological gap would be revealed. Here, German engineers took on the formidable task of scrutinizing every component, from the track tension to the transmission efficiency, striving to analyze and understand the capabilities of their adversaries' weaponry. The systematic testing and detailed documentation aimed to unearth truths about American industrial strength, vehicle durability, and engineering ingenuity. Truths that would inevitably lead to self-reflection and strategic reassessment in the weeks and months to follow. Performance, revealing a level of robustness that was quite impressive. Throughout their testing, the American engineers meticulously documented every detail, from the subtle nuances of the engine's response to different loads to the precise functioning of the transmission in real-world scenarios. Their comprehensive approach aimed not only to assess the immediate performance but also to predict long-term reliability under combat conditions. In the process of dismantling the various components for closer inspection, they observed patterns of wear and tear that defied the expectations rooted in German engineering principles. Where German tanks typically showed signs of stress after certain thresholds, the Sherman's parts demonstrated resilience beyond those limits, suggesting an overall sturdiness that could potentially translate into less frequent repairs and lower maintenance demands during prolonged engagements. A particularly striking discovery was how American manufacturing techniques, especially regarding the herringbone gear design, contributed significantly to this durability. While German engineers regarded such gears as too complex and costly to produce at scale initially, the Americans had already mastered mass production, turning this intricate design into a standard feature of their tanks. This ability to produce complex mechanical components efficiently and reliably in large quantities was a key advantage, enabling the Sherman to maintain consistency in quality and performance across thousands of units. The initial testing phase involved rigorous automotive trials, where the tank was subjected to obstacle courses intended to simulate the chaos and unpredictability of a battlefield environment. These tests measured fuel efficiency, tracked engine temperatures throughout different operational stages, and scrutinized how the transmission responded under various loads, whether crawling slowly over rough terrain or accelerating on open ground. After each of these tests, engineers carefully disassembled critical assemblies to analyze wear patterns, searching for early indicators of stress, insufficient lubrication, or potential design flaws that could compromise battlefield survivability. The findings from these examinations challenged the conventional wisdom held by German military engineers, who often balanced performance with strict reliability constraints. Contrary to this doctrine, the Sherman demonstrated a surprising level of operational endurance, maintaining its functionality over extended periods without frequent maintenance interventions. This capability was largely attributed to the way American engineering prioritized robustness and ease of operation over intricate precision that could be difficult to sustain in wartime conditions. Delving deeper into the powertrain, the examination uncovered significant differences in design philosophy. The Sherman's transmission, featuring 5 forward speeds and a single reverse gear with synchronized gear pairs from 2nd to 5th, exemplified a user-friendly approach. This synchronization eliminated the necessity for double clutching, a technique that required precise timing and considerable skill, making the tank remarkably accessible to drivers with basic automotive knowledge. In stark contrast, German tank operation demanded extensive training, as crews had to master complex double-clutching techniques along with delicate throttle adjustments to prevent transmission damage. The American design assumed a practical reality. Soldiers with standard mechanical skills could operate effectively, reducing the training burden and ensuring quicker deployment and operational readiness. This fundamental difference reflected broader strategic philosophies, one emphasizing simplicity and ease of maintenance, the other relying on highly trained specialists. Examining the engine, the Continental R975 Radial further highlighted the American approach to durability and versatility. This engine demonstrated exceptional tolerance to a wide range of operating conditions, maintaining consistent performance regardless of temperature fluctuations. While German engines often struggled under extreme weather, overheating or losing efficiency, the R975 proved resilient, a testament to its robust engineering. The engineers noted that even after prolonged use under demanding conditions, the engine continued to perform reliably, reinforcing their assessment of its superior tolerance and dependability. Throughout their detailed analysis, the American team appreciated this combination of innovative design, manufacturing techniques, and operational practicality, all of which contributed to a tank that not only matched but often surpassed German standards in key areas relevant to battlefield endurance and ease of use. Ultimately, their findings painted a clear picture of a vehicle engineered with a pragmatic focus, one that prioritized durability, simplicity, and mass production, rather than just raw performance, paving the way for the Sherman to become an enduring symbol of American industrial ingenuity during the war. Power. Despite its straightforward appearance, the cooling system was remarkably efficient, demonstrating a design that prioritized robust functionality. The air filtration system, in particular, proved adept at handling the dusty desert conditions, effectively preventing the frequent clogging issues that had plagued German tanks during their campaigns in North Africa. Every component of this tank reflected a design philosophy rooted in practicality, emphasizing reliability and ease of maintenance over complex theoretical improvements that might complicate manufacturing or field repairs. On the 6th and 7th of June in the year 1943, a significant event took place at the Hillis-Lien artillery range. Reich's Minister of Armaments, Albert Schaar, arrived to oversee a major demonstration aimed at showcasing the latest military technology. The event drew key figures from the armament industry, along with senior officers of the German Wehrmacht, all eager to observe and assess the newest developments. Among the scheduled activities were hill climbing trials in which German tanks competed directly against captured Allied vehicles, providing a clear comparison of maneuverability and performance under challenging conditions. During this demonstration, the American-made Sherman tank was positioned alongside some of Germany's most advanced armored vehicles, including a recent production model of the Panther, equipped with the powerful ACEF Diem turret, and a Ferdinand tank destroyer, representing the pinnacle of German armored fighting vehicle technology at the time. Schaar, tasked with overseeing the production of German armaments and directly accountable to Adolf Hitler himself, needed to gather critical information. His goal was to understand what the American industry was capable of producing and how German tank designs measured up against their enemy's equipment. The tests offered answers that neither Schaar nor the German tank designers could entirely accept easily. The Sherman, surprisingly agile, ascended the steep test slope with ease. Its manual transmission, which had 5 forward gears synchronized from 2nd through 5th, shifted smoothly without hesitation. The tank's engine delivered steady, reliable power throughout the ascent, giving the driver a sense of confidence and control that became a hallmark of the Sherman's user-friendly design. In contrast, the German Panther, powered by a formidable 700 horsepower Maybach HL 230 engine, managed to match the Sherman's performance by its sheer power but did so only with significant difficulty and relentless effort. Meanwhile, the Ferdinand, a heavily armed and armored vehicle weighing approximately 65 tons, was plagued by technical complexity, especially with its elaborate electric transmission system. During the trials, it became evident that the Ferdinand was incapable of conquering the steep incline. It stalled about halfway up. Witnessing this, Speer watched as recovery crews struggled to restart the immobilized tank. The embarrassment was palpable, especially as dozens of senior officers and industrial leaders observed. Many years later, in his memoirs, Speer would reflect upon the capabilities of the Sherman that he had seen during his inspection in Italy, in October of 1944. He noted that reports from the front lines had consistently praised the Sherman's impressive cross-country mobility, highlighting its ability to climb mountains that German tanks typically considered inaccessible. These reports attributed this remarkable performance to the Sherman's relatively powerful engine, whose output was well proportioned to the vehicle's weight. This combination afforded it superior off-road mobility on relatively flat terrain, a milestone German tank designers had historically struggled to achieve with their vehicles. The 26th Panzer Division had even specifically documented the Sherman's mobility advantage. This assessment by Germany's Minister of Armaments, documented in official reports and carrying significant weight within the Wehrmacht's circles, was later published in the newspaper Das Reich on June 27, 1943. The article praised the Sherman as one of the outstanding achievements of North American engineering laboratories and lauded it as a noteworthy product of the North American steel industry. It highlighted that the Sherman's design initially drew attention for its innovative features and practical strengths, which stood in stark contrast to the more complex and often less reliable German counterparts. Throughout the relentless development process, American engineers demonstrated a remarkable ability to meet and even surpass the demanding standards imposed by the North American automobile industry, which was known for its almost arrogant rigor. In particular, they embarked on pioneering efforts to create innovations such as the gyro-stabilized gun, a groundbreaking piece of technology hailed as the first of its kind anywhere in the world at that time. These advancements not only signified American ingenuity but also showcased a strategic edge in military technology, reinforcing the nation's position as a leader in innovative defense solutions. Publicly, American officials and military spokespeople issued carefully crafted statements highlighting these advancements, crafted in a way that served propaganda purposes, emphasizing American technological supremacy without explicitly revealing any vulnerabilities or setbacks. Nevertheless, behind the scenes, a different story was unfolding. A quiet wave of concern and alarm was spreading unchecked through the various engineering departments of Germany. Despite their pride in their engineering prowess, the Germans couldn't ignore the fact that their counterparts across the Atlantic were making significant progress that threatened their own operational and tactical superiority. American tanks, especially the renowned Sherman, were not merely sufficient for the demands placed upon them. Instead, they offered a fundamentally superior level of engineering designed specifically for sustained, reliable field operations. Back in the town of Kumdorf, a quiet hub of military research, a true system of rigorous testing persisted throughout the summer and into the autumn months of 1943. Engineers meticulously measured the operational ranges of the Sherman, conducting prolonged trials intended to push these vehicles to their absolute limits. Their records revealed astonishing findings. The Shermans could travel over 2,000 kilometers before requiring significant maintenance, a distance roughly 4 times greater than what the early Panther models could sustain under comparable field conditions. Furthermore, the data collected indicated that the Sherman's drivetrain achieved transmission efficiency levels that exceeded those of any German tank. Power losses through the transmission system were markedly lower, translating to more reliable and effective performance during combat scenarios and prolonged operations. Engineers also examined the vehicle's synchronized manual transmission, which was a marvel of simplicity and smoothness, demanding no double clutching or careful rev matching, unlike the German transmissions that often required such meticulous handling. This feature alone made the Sherman more user-friendly and less prone to operational errors in high-stress combat environments. Another noteworthy facet of the Sherman's design that raised eyebrows among German engineers was its final drive system. This component, responsible for transferring engine power to the tracks, challenged long-held German engineering assumptions. The Panther tanks, which inherited their final drive design from the earlier Tiger tank, relied on a system that was known to be prone to failure under stress. This design employed straight-cut gears within housings that proved insufficient to withstand the immense loads imposed by the 45-ton weight of the Panther itself. Such issues were not merely theoretical. German mechanics working on the North African and Eastern fronts often reported final drive breakdowns that forced tanks to be abandoned after relatively short movements, sometimes less than 100 kilometers. In stark contrast, the Sherman's final drives were constructed using a similar herringbone gear principle as the transmission, yet they rarely succumbed to failure. Even under the relentless pressures of sustained combat, conditions that would have quickly destroyed comparable German components, the Sherman's final drives proved remarkably resilient. Decades later, restoration projects for surplus Shermans revealed final drives that required no mechanical restoration after years of storage, attesting to a durability and design margin that far exceeded the immediate needs of wartime deployment. By late 1943, the team at Kumdorf had amassed sufficient data to produce comprehensive internal reports, which circulated across the technical branches of the Wehrmacht. These documents, intended for high-ranking officers and officials in the German Armaments Ministry, painted a clear and sobering picture of the comparative capabilities between the two nations' armored vehicles. They explicitly highlighted that the Sherman exemplified a level of automotive engineering maturity that Germany, despite its reputation for scientific rigor and technological knowledge, fundamentally lacked at that point in time. One of the most telling aspects of these findings was that the American approach to mass production favored tolerances that, by German standards, would appear somewhat imprecise or sloppy. Nonetheless, these tolerances contributed to a higher overall reliability and better field performance in real combat conditions. The interchangeable parts used throughout the Sherman fleet meant that field repairs could often be carried out with basic tools and minimal specialized training, greatly enhancing their operational sustainability and ease of maintenance. Such advantages underscored the stark contrast between American manufacturing philosophy, prioritizing practical reliability and ease of repair, and the meticulous, highly precise German manufacturing, which, despite its advantages in finesse, often struggled with durability under harsh battlefield conditions. While German military vehicles demanded meticulous factory-level craftsmanship and the use of highly specialized equipment for many repairs, their entire design philosophy fundamentally prioritized reliability and operational sustainability over achieving the highest possible performance metrics. Unlike some Western designs that often highlighted impressive technical specifications, German vehicles were engineered to remain functional and serviceable even under the most demanding combat conditions, where ease of maintenance and durability mattered far more than raw speed or maximum armor ratings. This pragmatic approach was rooted in their strategic emphasis on battlefield resilience, recognizing that in most scenarios, vehicles that could be easily repaired and kept in action would outperform those boasting impressive but impractical technical limits. Within Germany, internal engineering evaluations consistently documented observations about the advantages enjoyed by American industry. That extended well beyond mere manufacturing output or the quantity of produced units. American automotive engineering, built over decades of development in the civilian sector, provided a vast reservoir of technological know-how, manufacturing expertise, and standardized production techniques that Germany had not cultivated to a comparable extent. In the United States prior to the war, automobile ownership was widespread across all social strata, with vehicles being an integral part of everyday life for millions of ordinary citizens. The American automotive industry had established a production model based on mass manufacturing, interchangeability of parts, and a rigorous quality control system that allowed for rapid, cost-effective assembly and straightforward repairs. In stark contrast, Germany's civilian automotive experience was considerably more limited. Cars remained predominantly symbols of luxury, accessible only to the wealthier classes and influential party elites. The ambitious Volkswagen project, which promised affordable transportation for ordinary Germans, had been underway since 1934 but had produced fewer than 1,000 civilian vehicles by 1939. This relatively modest level of civilian automotive development meant that German engineers and mechanics lacked the extensive experience and infrastructure that had become commonplace in America. Consequently, German tank design reflected this disparity. American tanks were engineered with the typical mechanic in mind, vehicles that could be maintained and repaired by personnel whose skills were already familiar with civilian automotive principles. Conversely, German tank designs demanded highly specialized training, with maintenance requiring expert technicians with years of military-specific technical expertise. As field reports from the front lines accumulated through late 1943 and into 1944, the disparity in reliability between German and American armored vehicles became starkly apparent. The Panther tank, for instance, was plagued by operational restrictions aimed at preventing mechanical failures that could strand the vehicle in the field. Operators were explicitly instructed to avoid frequent gear changes, as shifting gears excessively could damage the transmission, a critical and costly component. The third gear in particular was prone to breakage, prompting field manuals to advise its use only when absolutely unavoidable. Additionally, Panthers could not turn while reversing because this action would destroy the transmission. Tactical maneuvering was therefore limited, requiring careful ground resistance balance on both tracks for pivot turns. Foreign objects or debris entering the running gear could cause jams in the drive sprocket, often necessitating hours of maintenance and inspection to restore proper function. These persistent mechanical issues persisted despite the fact that Panthers were produced in dedicated, specially equipped factories staffed by highly skilled German workers, using the best materials available within the Reich. The emphasis was on maintaining strict quality standards. However, the intricate complexity of these tanks placed high demands on maintenance and operational discipline. By contrast, the American-designed Sherman tank exemplified the advantage of integrating civilian automotive engineering principles into military hardware. The Sherman's design team included engineers from major industrial giants such as General Motors, Ford, and Chrysler, who applied decades of civilian mass production experience. Wherever possible, the Sherman incorporated commercial automotive components, leveraging established supply chains and manufacturing processes. Its transmission system, for example, was sourced from multiple manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, each building to identical specifications with interchangeable parts that could be swapped without recalibration, simplifying maintenance and repairs in the field. This high degree of standardization and modularity, routine in American automotive manufacturing, was only beginning to be understood or implemented in German tank production. The American approach facilitated quicker repair times, reduced logistical burdens, and enhanced operational readiness, all of which translated into a tangible battlefield advantage. Meanwhile, German vehicles remained heavily dependent on precision assembly and specialized parts, which, despite their quality, were more susceptible to breakdowns and more difficult to repair quickly under combat conditions. In the realm of tank manufacturing during the wartime period, a notable characteristic was the deliberate introduction of nuanced modifications by various manufacturers. These subtle differences rendered the true interchangeability of spare parts practically impossible, complicating logistical support and maintenance efforts across Allied and Axis forces alike. Over the course of 1943 and 1944, additional captured Shermans made their way to the military depot at Kumdorf. These included tanks seized from British units in Italy and from Soviet forces along the Eastern Front, each with their own history and modifications. Every captured vehicle was subjected to a rigorous and standardized testing regime, which aimed to gather a wealth of data concerning their operational capabilities. This process contributed profoundly to the development of a comprehensive database, chronicling the performance of American tanks in their various configurations and across different production runs. Meanwhile, the British, seeking to enhance the Sherman's battlefield effectiveness, had retrofitted some of these vehicles with their famed 17-pounder anti-tank gun. This adaptation gave rise to the so-called Firefly variant, which effectively addressed the Sherman's primary shortcoming: its relatively modest firepower when confronting heavily armored German tanks. German engineers, ever keen on understanding their adversaries' technological advancements, examined these modified Shermans with a keen eye. Remarkably, they observed that the Sherman's large turret ring was capable of accommodating the significantly larger British gun with only minimal structural modification. This insight revealed a latent potential embedded within the original design, a flexibility that the engineers had not originally anticipated. The Firefly's successful integration underscored an unexploited capability that had implications for future tank development and adaptability. Meanwhile, the Panther, engineered swiftly in response to the threat posed by Soviet T-34 tanks, faced significant restrictions regarding upgrades to its armament. Any attempt to enhance its firepower required a complete redesign of its turret and other structural components, making incremental improvements unfeasible. To better understand the Panther's mechanical robustness, the military initiated an extensive automotive testing program. These tests included durability trials meticulously designed to simulate the rigors of combat environment, with engineers driving Panthers over hundreds of kilometers of rough, cross-country terrain. Every mechanical issue that arose, ranging from minor glitches to major failures, was carefully documented along with details of the maintenance required and parts that needed replacement. These reliability assessments were then compared with field reports from Panther and Tiger units operating on both the Eastern Front and Italian theaters. The results painted a clear and troubling picture. Reliability and operational readiness were considerably lower than ideal. Throughout most of 1943, Panther units struggled with an average operational readiness of less than 40%. Some battalions reported catastrophic failure rates as high as 25 to 30%, with fewer than 1 in 5 Panthers being combat capable at any given time. In stark contrast, the Shermans maintained far higher operational availability across all theaters, consistently demonstrating greater reliability. German field reports detailed these problems with particular severity, pinpointing the Panther's critical reliability issues. For instance, during the pivotal Operation Citadel at Kursk in July of 1943, the Panthers achieved a dismal 16% operational readiness. Mechanical failures in these tanks often caused more tanks to be lost or rendered unusable than the direct damage inflicted by enemy fire. Over the following months, the situation showed some signs of improvement. By December of 1943, the Panthers' readiness had risen modestly to 37%. In February of 1944, similar figures persisted, but by April, the statistic increased to 50%. The most significant leap came in May of 1944, when the operational readiness of Panthers reached 78%, marking a notable improvement. These figures represented not the total number of Panthers in service, but rather the proportion that were fully operational and ready for combat on any specific day. The remaining tanks were either awaiting parts, under repair, or sidelined due to mechanical deficiencies. This gradual, incremental progress illustrated ongoing efforts by engineers and manufacturers to rectify the inherent design flaws that had plagued the Panther since its inception. Nevertheless, even at its peak, Panther readiness rates never approached the consistent, high reliability displayed by the Sherman tanks from the initial stages of production. By the end of 1943, it had become clear to any objective analyst that a pattern of reliability disparity was developing. The data clearly indicated that the Sherman's diesel engine, when properly maintained, had an operational lifespan exceeding 3,000 kilometers, making it suitable for prolonged combat use. In comparison, the Panther's gasoline engine, which was hastily designed and built to meet urgent wartime demands, barely managed to reach 1,000 kilometers before requiring major overhaul or replacement, an alarming discrepancy that had serious implications for operational deployment, logistical planning, and overall battlefield effectiveness. Following a series of targeted improvements, the most critical early issues that hampered operational effectiveness were systematically addressed. By March of 1944, German reports acknowledged that the upgraded Panther engines had achieved a notable service life, capable of enduring between 700 and 1,000 kilometers before requiring major overhaul. This achievement was viewed as a significant success, though it still fell considerably short of the reliability demonstrated by the American Sherman tanks. In fact, these Panther engines reached only about a third of the performance level of the diesel engines used in Shermans, which had been renowned for their durability and ease of maintenance. The maintenance demands of the Sherman transmissions further highlighted the differences between the two tanks. Sherman transmissions required very little attention during routine operations, thanks largely to their synchronized gear systems that substantially reduced the likelihood of driver error causing mechanical damage. This design allowed crews to operate the tank more confidently and with fewer worries about damaging the transmission, even after extensive use. In stark contrast, Panther transmissions demanded constant vigilance and frequent repairs. Third-gear failures were so common in Panther tanks that drivers had learned to skip directly from second to fourth gear while driving, carefully avoiding the problematic third gear to prevent breakdowns and keep the tanks operational in the field. In terms of durability under combat conditions, the final drives of the Sherman proved reliably robust, even when subjected to the harsh realities of battle, which routinely destroyed Panther final drives within a window of only 100 to 200 kilometers of operation. German units operating captured Shermans provided invaluable first-hand data, supplementing the findings from Kumdorf testing with insights from actual battlefield conditions. These mechanized units, desperately seeking dependable vehicles as their own tanks and infantry formations degraded in quality, eagerly adopted any intact American tanks they could obtain. The deployment of captured Shermans not only bolstered their operational capacity but also demonstrated the practical superiority of the Sherman's mechanical reliability. In contrast to the Soviet T-34 tanks, which Germans often modified extensively before deploying them in combat, the Shermans entered German service largely in their original form. They did not require any fundamental modifications because they functioned correctly as designed, without any significant flaws or deficiencies needing correction. German tank crews who had experienced repeated mechanical failures in their own vehicles found the Sherman's reliability to be a stark and welcome contrast. Many of these crews expressed their appreciation through reports and letters, frequently noting how the Sherman's dependable performance allowed them to concentrate on tactical considerations rather than incessant maintenance. The results of these reliability differences became particularly evident in operational reports from panzer regiments. Sherman crews could focus their efforts on tactical planning, maneuvering, and maximizing combat effectiveness, knowing their tanks would operate reliably throughout their missions. Meanwhile, crews of Panther and Tiger tanks constantly worried about potential breakdowns, anxious that they might not reach the battlefield or complete their assigned tasks before mechanical failures immobilized their vehicles. This persistent concern underscored the importance that reliable mechanical performance held in the final stages of the war. During the German counter-offensive at Hellesheim in January of 1945, the 10th SS Panzer Division captured 12 M4A3 Shermans that had belonged to the American 43rd Tank Battalion. These tanks were seized intact, having been abandoned by their crews amidst the chaos of the German assault. The captured Shermans were quickly organized into the 13th Company of the 10th SS Panzer Regiment, where they served in combat for the remaining months of the conflict. Their roles included reconnaissance and mobile reserve functions, both requiring tanks that could sustain prolonged movement without frequent maintenance and rely on consistent mechanical performance to ensure mission success. German commanders recognized the significance of the findings from Kumdorf testing conducted years earlier. It had been demonstrated conclusively that American tanks, particularly the Shermans, could be depended upon to perform reliably under combat conditions when the situation demanded it. In many ways, this dependability proved more crucial than raw firepower or armor protection, especially in the closing months of the war, where operational reliability could determine the outcome of engagements and the mobility of entire units. By the beginning of January of the year 1944, the German military expanded its testing programs to include captured equipment and additional assessments of the Sherman designs. As the Wehrmacht retreated across multiple fronts, these efforts provided further insights into the tank's performance. Engineers, for example, began examining the M4A1 variant fitted with the Continental R-Negnan radial engine, among other models, to better understand their mechanisms and durability in the field. These continued efforts underscored the growing appreciation among German military planners that, regardless of the formidable adversary's firepower, the true tactical advantage increasingly depended on the reliability and operational readiness of the equipment. In summary, throughout the course of the war, the American Sherman tank emerged as a symbol of mechanical dependability. Its ability to arrive at the battlefield ready to engage, with its main gun fully operational and its components functioning flawlessly, far exceeded the performance of many German tanks, even those with superior firepower. The persistent reliability of the Sherman, especially when contrasted with the more fragile Panther in the detailed assessments carried out during this period, engineers meticulously examined the various renditions of the Sherman tank to understand their distinctive features and how they compared with other contemporary armored vehicles. One notable focus was on the M4A2 variant, which was powered by twin General Motors 6046 diesel engines. Experts observed that this particular model outperformed many of its counterparts in fuel efficiency, a crucial advantage given the wartime scarcity of resources. The distinct operational qualities of the diesel-powered M4A2 set it apart from other variants, highlighting its ability to deliver sustained performance with less fuel consumption. In parallel, the evaluators also examined the M4A3 variant equipped with the Ford GAV8 gasoline engine, a power plant that had earned the high regard of American crews. Many soldiers in the U.S. Army considered the GAV8 to be the most reliable and well-designed engine used in Sherman tanks, attributing to it a reputation for durability and consistent performance under arduous battlefield conditions. What was remarkable across all these variants was a shared core characteristic, an exceptional level of automotive reliability rooted in robust engineering principles and meticulous manufacturing practices. Regardless of differences in power plants or specific modifications, each tank maintained a dependable operational profile. This consistency was especially striking to German engineers, who, during the war, had grown accustomed to significant inconsistencies in quality across various manufacturers, some producing vehicles that barely met minimum standards, others delivering more reliable machinery. The uniformity and dependability exhibited by the American tanks, regardless of their version, thus left a deep impression on German experts. Particularly noteworthy was the performance of the diesel-powered M4A2, which impressed German military engineers during their inspections in the town of Kumdorf. Throughout the war, Soviet forces received a considerable number of these tanks through Lend-Lease agreements, specifically, around 4,100 units, and some of these inevitably fell into German hands during retreats on the Eastern Front. The twin GM 6046 diesel engines in the M4A2 demonstrated a capability on par with any other Sherman variant, but with a significant edge. They consumed considerably less fuel than the gasoline engines used in other tanks. This was a crucial benefit as the German army faced rapidly diminishing fuel supplies, making fuel efficiency an increasingly vital aspect of wartime logistics. It is important to note that, prior to this, German engineers had explored the possibility of integrating diesel engines into their own tanks. However, these efforts were ultimately abandoned due to the severe manufacturing difficulties involved in the complexity of developing reliable fuel injection systems suitable for armored vehicles. Meanwhile, American industry succeeded in producing both diesel and gasoline Sherman tanks simultaneously, without causing disruptions to their overall production schedules. This ability underscored the advanced manufacturing flexibility and technological sophistication of the United States, capabilities that German industry struggled to match under the stresses of wartime production. By March of 1944, reports from General Heinz Guderian, who served as the Inspector General of Panzer Troops, indicated a degree of progress in the maintenance and reliability of German tanks, particularly the Panther. Official communications at that time noted that improvements had brought Panther reliability up to what was termed an acceptable standard, an achievement that, while commendable, was a sign of how far the Germans had fallen behind their Allied counterparts. The life expectancy of the Panther's engine had increased to roughly 700 to 1,000 kilometers, and most of the persistent issues with the final drive had been largely addressed thanks to targeted design modifications and improvements in manufacturing quality. This marked a noteworthy milestone, as such levels of reliability were, at best, what American tanks had demonstrated since their initial deployment in 1942. The Germans considered their tanks to have reached a certain baseline of functionality comparable to Allied standards, yet the truth was that their armored vehicles had been lagging in reliability and effectiveness for quite some time. The German military publicly celebrated this supposed achievement, but it served only to underscore how much the development gap between German tanks and the American Sherman line had widened. This disparity became even more evident against the backdrop of increasing resource shortages and the relentless Allied strategic bombing campaign targeting critical manufacturing hubs. The German war effort was increasingly strained by these pressures, which hindered tank production and technological innovation. Allied air raids targeted key nodes in the German armored vehicle supply chain, aiming to cripple the capability to produce new tanks and upgrade existing ones. One of the most damaging attacks occurred in late April of 1944, when Royal Air Force bombers launched a large-scale raid on the Maybach engine plant located in Friedrichshafen. This attack involved over 322 aircraft, making it one of the most destructive airstrikes on German tank manufacturing during the entire war. The Imperial War Museum archives describe this raid as the single most damaging assault on the German tank industry, effectively crippling the production capacity of the plant for a significant period. The raid not only destroyed the Maybach factory itself but also resulted in the obliteration of the adjacent ZF gearbox plant, an essential component manufacturer crucial for the assembly of tanks. As a consequence, the production of tank over the course of approximately 6 months, the situation within the German tank industry deteriorated markedly. When production finally picked up again in late November of the year 1444, it was evident that the quality control systems had suffered a severe decline. The relentless demands of war and the shift towards utilizing slave labor, an increasingly common practice as German workers were conscripted into the military, had introduced many detrimental shortcuts and deliberate acts of sabotage into the manufacturing process. For instance, Workers sometimes jammed cigarette filters into oil passages, clogging critical lubrication systems, while gasket installation was often performed incorrectly, leading to leaks and compromised sealing. Furthermore, components were assembled with insufficient clearances, which severely impacted the reliability and lifespan of the tanks. These production flaws, however, never affected the tanks produced in American factories. Such plants, clearly located far from combat zones, benefited from highly motivated workers earning fair wages and working under conditions that promoted quality. The key difference between the American and German approaches to tank manufacturing was less about technical engineering knowledge, which was comparable in both nations, and more about the industrial capacity, organization, and underlying design philosophies that guided their production efforts. German engineers possessed a thorough understanding of automotive principles, supported by extensive theoretical knowledge and scientific expertise. Despite this, their approach to applying these principles was inconsistent, as they often prioritized certain performance characteristics, such as armor and firepower, over aspects of reliability and ease of maintenance. This emphasis on impressive specifications often came at the expense of operational dependability in actual battlefield conditions. Take, for example, the Panther tank. Its formidable 75mm KWK-42 gun and heavily sloped frontal armor were designed to outperform many of its adversaries visually and on paper. Yet, this same emphasis placed a tremendous strain on the vehicle's powertrain, which was not engineered to support the hefty 45-ton weight reliably. Similarly, the Tiger tank's advanced capabilities came with steep maintenance demands. It required complex procedures and the expertise of highly trained mechanics to keep it operational, and frequent repairs were often unavoidable. Such trade-offs might have been tolerable if German industry had the capacity to produce enough tanks and spare parts to keep these machines operational in sustained combat. However, this was simply not the case. As Allied bombing campaigns intensified and shortages of raw materials became more severe, the German war machine's ability to produce and maintain these advanced tanks was severely hindered. By contrast, American engineers, who had decades of experience in civilian automotive manufacturing, designed their tanks with mass production and ease of maintenance as fundamental principles. The Sherman tank epitomized this pragmatic approach. Its powertrain comprised components that had already proven reliable in civilian vehicles, such as trucks and cars. The design borrowed heavily from established automotive practices, enabling rapid, large-scale production and straightforward repair procedures. Notably, American tanks featured electrical systems that included a backup generator capable of powering the turret traverse even if the main engine failed. A seemingly minor luxury to German designers, but one that proved critical in combat situations. German tank crews could only dream of such features, especially those who had experienced the frustration of turret traverse failures when their engines stalled during uphill movements. German technical specifications rarely included such conveniences because their design priorities centered around armor thickness and firepower, considering other factors secondary. As a result, the typical German tank was optimized for battlefield performance in theory, but often fell short under the realities of wartime operational stress. By the spring of 1944, reports from Vermont units across all fronts indicated an increase in mechanical problems, a direct consequence of declining manufacturing standards and the dwindling availability of spare parts. The Panther tanks, for example, when required to be transported over long distances, had to be moved by rail because their final drives were unable to withstand the stresses of sustained road marches. Field commanders issued explicit orders limiting their movement, understanding that the tank's mechanical fragility made extended marches on roads too risky, further hampering operational flexibility. In summary, the disparity between the manufacturing philosophies of Germany and the United States was stark. While German industry, with its sophisticated scientific knowledge, aimed for top-tier specifications and battlefield dominance, it lacked the industrial capacity and organizational efficiency needed to sustain such a strategy over the long term, especially under the relentless pressure of Allied bombing and raw material shortages. Conversely, American industry, built on a foundation of civilian automotive experience, prioritized reliable, easily producible, and maintainable tanks that could be manufactured in the tens of thousands and kept operational by mechanics with only basic training. This pragmatic approach, emphasizing mass production and field serviceability, played a decisive role in shaping the effectiveness and availability of Allied armored forces during the Second World War. During World War II, the importance of reliably transporting tanks to the battlefield became increasingly evident, as many vehicles succumbed not to enemy fire but to mechanical failures during long approach marches. To address this, specialized recovery vehicles were developed to assist and recover disabled tanks on the front lines. For instance, the Berger Panther, a recovery vehicle built on the same Panther chassis as the combat tanks it was designed to support, was intended to help stranded Panthers return to action. However, these recovery vehicles suffered from the same fundamental reliability issues as the tanks themselves, underscoring a recurring problem for the German Wehrmacht. German commanders faced a harsh reality. Mechanical failures often caused greater losses than enemy combatant actions. Some units reported that as much as 70% of their tank losses stemmed from mechanical breakdowns rather than direct combat damage. This prevalence of mechanical issues became a significant obstacle, limiting operational effectiveness and reducing the overall impact of German armored forces on the battlefield. Meanwhile, the Allies, particularly the United States, maintained an extraordinarily high rate of tank production that outstripped Germany's industrial capacity by a wide margin. American factories churned out over 49,724 Sherman tanks during the war, a volume that surpassed the entire spectrum of German tank production, covering all tank types by a considerable margin. These figures highlight the scale of American industrial effort and the relentless focus on ensuring that additional tanks reached the front lines. The British Commonwealth forces also benefited from extensive supplies of Shermans, delivered through Lend-Lease agreements, which significantly bolstered Allied armored strength. The Soviet Union, seeking to enhance its armored fleet, received more than 4,000 diesel-powered Sherman variants. Meanwhile, in the jungles of Burma, Chinese forces used Shermans to devastating effect against Japanese tanks, which were, at the time, both poorer in technological sophistication and inferior in armor and firepower compared to their American and German counterparts. The widespread deployment of Shermans across various theaters of war consistently validated the findings from testing conducted earlier by officers like Colonel Kummersdorf, which underscore the vehicle's robustness and dependability. When properly maintained, the Sherman proved capable of operating effectively in a wide range of harsh conditions that would have nearly immobilized or destroyed German tanks. German tank crews who captured and later operated Sherman tanks often expressed high praise for their automotive engineering. They acknowledged that, in terms of mechanical reliability, the Shermans were superior to many German designs in their operational environments. In particular, German mechanics on the Eastern Front found the complex Chrysler 57 multi-bank engine, an engine with 5 separate engine blocks, easier to troubleshoot than German tanks' engines, which typically demanded specialized knowledge and equipment for repairs. This Chrysler engine, despite its complexity, was appreciated for its relatively straightforward maintenance compared to German engines, which often required meticulous adjustments of valve clearances, ignition timing, and carburetor settings. The Ford GAA V8 engine, widely lauded by Allied crews for its exceptional reliability and power output, appeared to German mechanics as remarkably dependable. They contrasted it with the Maybach engines prevalent in German tanks, which frequently needed constant adjustments and fine-tuning to maintain optimal performance. The Ford engine was known for delivering a consistent power supply without frequent maintenance, a critical advantage during long campaigns. Similarly, the General Motors twin diesel engine, initially rejected by the U.S. Army because it was perceived as less reliable than gasoline-powered engines, proved to be far superior in practice. It consistently outperformed German diesel engines used in tanks, demonstrating greater reliability and sustained performance. This was particularly impressive considering that the twin diesel was primarily produced for Lend-Lease shipments, yet it showcased the advantages of American diesel technology. The design choices built into the Sherman tank, notably its generous safety margins, offered considerable operational benefits. For example, the basic transmission and final drive components initially designed for the standard 30-ton M4 tank with 400 horsepower required no significant modifications to accommodate the heavier 42-ton M4A3E2 jumbo assault tank, an upgraded version with substantially increased armor protection. The same components, initially intended for lighter tanks, successfully transmitted up to 650 horsepower from experimental engines without any failures or need for reinforcement. German engineers, in their analysis, often viewed this overbuilding, using more robust components than strictly necessary, as inefficient, considering it as wasteful of resources and increasing production costs. They believed that such excess capacity added to the use of scarce materials and did not provide immediate battlefield benefits. However, American engineers understood that these extra margins of safety and robustness served as vital future-proofing measures, allowing for potential upgrades and more reliable performance throughout the vehicle's lifespan, ultimately proving to be a worthwhile investment. By the summer of 1944, this philosophy of over-engineering and reliable design had already demonstrated its value on the battlefield, contributing to the durability and effectiveness of Allied armored forces in one of history's most demanding conflicts. During the tense days leading up to the Allied invasion of Normandy, the tank commanders of the German Wehrmacht were acutely aware that their technical shortcomings went far beyond the limitations of individual vehicles. These commanders understood that, despite the formidable appearance and tactical prowess of their tanks, they were facing an adversary equipped with strategic advantages that rendered physical specifications only a part of the larger picture. American artillery, renowned for its destructive power, coupled with overwhelming close air support and a logistical network capable of supplying armies with seemingly inexhaustible resources, created a formidable barrier for German armored units. These factors collectively made it incredibly difficult for German tanks, no matter how well designed or well led the tactical formations, to stand firm against the relentless onslaught of the Allies' combined arms approach. However, one aspect that distinctly favored the Americans was the remarkable reliability of their tanks, particularly the M4 Sherman. Thanks to their robust engineering and consistent performance, American armored units could operate with a level of persistence and endurance that German panzer divisions, burdened by mechanical weaknesses, simply could not sustain over protracted campaigns. While German tanks often required meticulous maintenance and were plagued by mechanical failures, the Shermans stood out as dependable workhorses capable of maintaining continuous operational tempo. This reliability meant that American tank battalions could frequently launch offensive maneuvers, carry out sustained combat operations, pursue retreating enemies, and quickly reconfigure for subsequent battles, all without the frequent, time-consuming stops for repairs that hampered their German counterparts. In contrast, Panzer divisions had to manage their limited vehicle stock with extreme caution, carefully rationing their operational tanks because each movement and action drained precious service life from their already fragile components. Every tactical decision weighed heavily on the finite life remaining in their vehicles' parts, as reckless use could lead to mechanical breakdowns and, ultimately, loss of vehicles that might otherwise have been decisive on the battlefield. Such operational restrictions severely limited the attacking potential of German armored units, forcing them into a defensive stance or necessitating careful conservation of their limited resources. From the German perspective, the superiority of American automotive technology became increasingly evident as the war progressed, particularly when they attempted to utilize captured Allied equipment. For example, in December 1944, during the Battle of the Bulge, the 150th Panzer Brigade, specifically established to infiltrate Allied lines and disrupt their supply routes, sought to acquire captured American tanks as a means of deception and increased firepower. The Germans believed that the renowned reliability of the Sherman tanks would give them a crucial edge in covert operations behind enemy lines. However, despite their hopes, the brigade only managed to secure 2 Sherman tanks, and out of those, only one was in fact capable of reaching operational status. Unfortunately, even this serviceable Sherman never saw combat, as the infiltration mission was severely hampered by massive traffic jams and logistical delays, preventing the operation from achieving its strategic aims. In the context of executing behind-the-lines sabotage or infiltration missions, tasks that demanded vehicles capable of operating flawlessly without breakdowns over extended periods, American equipment again proved superior. The reliability of their tanks increased the chances of mission success where mechanical failure could spell failure or capture. German tanks, no matter how well maintained or fully operational, struggled to provide this level of dependability. This persistent deficiency was so apparent that by late January of the year 1945, the German military leadership was forced to admit their automotive difficulties openly. On the 23rd of January, representatives of the Panzer Commission convened and produced a comprehensive report that revealed catastrophic failures in the final drives of all German tank models. This document laid bare the extent of the problem, detailing the widespread breakdowns that had become commonplace. Prior to the offensive in the eastern theaters of battle in that same year, there had been approximately 500 failures in the final drives of the Panzer IV tanks, 370 in the Panther tanks, and about 100 in the Tiger tanks. Likewise, failures had been reported in other specialized vehicles, including the Hetzer tank destroyer, which was built on the Czech 38-ton chassis, suffering around 200 similar malfunctions. The consequences of these mechanical failures were dire and well understood by high-ranking officers. Lieutenant General Wolfgang Tamal, Chief of Staff of the Panzer Troops and acting under the orders of the Inspector General of Panzer Forces, explicitly described the operational impact in stark terms. In such circumstances, the ability to manage tanks efficiently and systematically was severely compromised. Mechanical unreliability meant that crews gradually lost confidence not only in their vehicles but also in their own safety, leading in some cases to abandoning entire tanks to avoid being stranded and captured by advancing enemy forces. German tanks, once symbols of intimidation through their formidable appearance and advanced engineering, were increasingly viewed as liabilities, hampered by an array of mechanical flaws that undermined their battlefield effectiveness and morale. Ultimately, the technological shortcomings and mechanical unreliability of German tanks deeply affected their tactical use and the overall strategic stability of their armored units. These persistent issues underscored the fundamental shortcomings in the design specifications of armored vehicles became glaringly evident through the most basic yet critical requirement: mechanical reliability. This essential trait, ensuring that tanks could reliably reach the battlefield, endure the rigors of combat, and complete their missions, was sorely lacking. By early 1945, as Soviet forces relentlessly advanced toward Berlin, the Kumdorf testing facility found itself facing an urgent necessity for evacuation. Engineers there worked frantically, hurriedly packing vital testing data and shipping critical documentation to more secure facilities further westward. Their aim was to salvage as much technical intelligence as possible, anticipating that their work might prove invaluable for post-war analysis. Amidst the chaos of retreat, some of the captured tanks, which included at least 2 of the American-made Shermans, were pressed into makeshift service with increasingly desperate German units. These units fought fiercely, battling to defend strategic approaches to Berlin, and in the process, these foreign-designed tanks fought alongside the German military equipment, providing a rare opportunity to compare different engineering philosophies under actual combat conditions. The Sherman tanks continued in active service until they were either destroyed by enemy fire or abandoned once their fuel supplies depleted. Meanwhile, German tanks, such as Panthers and the scant remaining Tigers, began to falter at alarmingly high rates due to mechanical failures, a reality that even seasoned crews, accustomed to poor reliability, found shocking. The saga of War Daddy 2, alongside dozens of other Shermans tested at Kumdorf, starkly illustrates one of the most significant industrial disparities of the Second World War. German engineers, operating within an industrial system that prioritized theoretical perfection and impressive specifications over practical utility, produced tanks that appeared formidable and advanced on paper but ultimately failed to perform reliably during sustained field operations. Conversely, American engineers, leveraging decades of experience in automotive manufacturing and applying these principles to military vehicle design, produced tanks that, despite lacking some elements of technical sophistication, proved remarkably dependable under the variable and often harsh conditions of combat. In armored warfare, as in all facets of military operations, the effectiveness of a weapon hinges on its ability to function when genuinely needed. The tank that reliably operates in the chaos of battle will invariably outperform the theoretically superior weapon that fails to reach its target or breaks down prematurely. Post-war analyses conducted by American and British intelligence agencies validated what the tests at Kumdorf had demonstrated. German tanks, which had initially been admired for their impressive specifications, frequently succumbed to mechanical failures just as often as they did to enemy action. Investigators uncovered that the final drives often broke under stress, transmissions seized due to poor lubrication or operator errors, and engines burned out from overheating or oil starvation. The German obsession with creating vehicles of unmatched individual superiority and spectacular specifications blinded their designers to a vital truth: that reliability and ease of maintenance were more crucial than just raw performance. Their tanks, though mechanically advanced on paper, were often so complex that no ordinary conscript mechanic could repair them without extensive, specialized training. The engines installed required constant expert oversight by skilled technicians, and the logistical systems supporting these vehicles were overwhelmed by the sheer number of unique parts needed, distributed widely across scattered units, making effective maintenance nearly impossible under wartime conditions. The lessons learned through the rigorous testing at Kumdorf profoundly influenced post-war German tank design philosophy. When West Germany launched the development of its first main battle tank, the Leopard 1, during the 1950s, the designers consciously shifted their focus. They prioritized reliability and maintainability, principles that had become glaringly obvious through the dismal performance of earlier models, over the pursuit of raw specifications and impressive but impractical features. This strategic orientation marked a significant departure from the earlier German approach, embracing practical engineering solutions that emphasized functional dependability over superficial performance on paper. The performance standards established during this period reflect a deliberate and focused effort to learn from and adapt proven engineering principles, particularly those originating from American automotive design. These principles were thoughtfully integrated into the development of military vehicles, leading to the creation of the Leopard 1 tank, a machine that embodied many of the successful design philosophies that had contributed, alongside other factors, to the legendary reputation of the Sherman tank. The Leopard 1 featured a robust powertrain, built with generous safety margins to ensure durability and resilience under combat conditions. Its design emphasized ease of maintenance, eliminating the need for specialized tools, which significantly reduced downtime and simplified repairs in the field. Moreover, the use of standardized components allowed crews to perform rapid repairs and facilitated future upgrades without requiring a complete redesign of the tank's structure. As a result, the Leopard 1 emerged as one of the most successful tank designs of the Cold War, serving with numerous armies across different nations and remaining in continuous production for many decades. The collection of captured Sherman tanks at Kummersdorf, including the distinctive War Daddy II, whose name was still prominently painted on its hull, symbolized far more than a simple collection of enemy equipment for technical analysis. These tanks stood as living evidence that the maturity of industrial infrastructure and the application of sound engineering principles, grounded in practical combat experience, were ultimately more critical to military success than the pursuit of cutting-edge technological innovations pursued in isolation from manufacturing realities. The German tank designers, motivated by the belief that superior specifications and advanced technology could compensate for material disadvantages and fewer numbers, had pursued increasingly sophisticated designs. However, their assumptions proved flawed, as reliability, maintainability, and logistical support became decisive factors on the battlefield. Conversely, American tank designers, through hard-won lessons from real combat conditions, prioritized building reliable, easily maintainable vehicles. They understood that sustained operational availability, supported by effective logistics and maintenance, ultimately determined victory in modern mechanized warfare. Their approach proved more effective, and history demonstrated it decisively. The reliability gap between the Sherman and German tanks not only influenced tactical armored engagements but also shaped broader strategic understanding. It underscored how military industrial capacity and pragmatic engineering could decide conflicts far beyond individual battles. While Germany entered World War II with technological advantages in many weapon systems, boasting advanced scientific knowledge and engineering expertise that initially outstripped most opponents, they lacked the industrial depth and manufacturing sophistication necessary to sustain those technological advantages through mass production over prolonged periods. The United States, in contrast, entered the war with weapons that, while often less technically advanced in specific aspects, benefited from immense industrial capacity. This capability allowed them not only to produce vast quantities of equipment but also to continuously refine quality, reliability, and performance based on ongoing combat feedback. The industrial model exemplified by the Sherman tank's design and manufacturing process proved significantly more effective than relying solely on advanced German technological concepts applied in small-scale production. By the end of the conflict, the United States had produced nearly as many Sherman tanks as Germany had produced all classes of tanks combined, while also manufacturing and supplying enormous quantities of other weaponry. This extensive industrial effort supported allies through programs like Lend-Lease and contributed to a level of military readiness and economic stability unmatched among the fighting nations. Such industrial and economic resilience played a decisive role in the outcome of the war, arguably as influential as any single battlefield victory. The capacity to sustain large-scale, rapid production of effective weaponry, to adapt and improve those weapons continuously, and to support a broad coalition of allies, endowed the United States with a form of strategic superiority that Germany and other Axis powers could not match. This combination of industrial might, practical engineering, and economic stability ultimately shaped the course of the conflict itself, reaffirming the importance of manufacturing capacity and logistical support in modern warfare's complex tapestry. The fundamental truths of tank performance and efficiency became undeniably clear once examined through an objective lens, truths simple in their logic but devastating in their implications. Consider a Sherman tank armed with a 75mm gun that consistently reached the battlefield ready to fight and fought effectively. Such a vehicle was infinitely more valuable on the modern battlefield than a Panther, equipped with a superior gun, which, despite its advanced specifications, often broke down before engaging the enemy or required several days, sometimes up to 3, to be repaired for every single day it was in active operation. This disparity in operational reliability had profound strategic consequences. An entire battalion, comprising 100 tanks, maintaining an efficiency rate of at least 80% in operational status could carry out missions that a similarly sized unit, with only about 40% of its vehicles functioning properly, would simply lack the capability to attempt. In essence, reliability was no mere convenience or minor technical detail. It fundamentally underpinned the very effectiveness of armored units in real combat scenarios. Throughout the duration of the war, German tanks consistently failed at this critical criterion, falling short of the basic requirement of operational dependability. Conversely, American tanks constantly demonstrated the capacity to pass this essential test. By the middle of 1943, exhaustive testing at the Kundorf Proving Grounds had clearly proven this point beyond any reasonable doubt. Meanwhile, German commanders persisted in deploying Panthers and Tigers, vehicles that, despite their intimidating appearance and impressive technical specifications, could not be relied upon to perform when most urgently needed. These tanks often suffered from mechanical failures that rendered them ineffective at crucial moments. The victory of the Sherman tank during World War II did not hinge on having the most powerful gun or the thickest armor, although it was no slouch in those areas, but on a far more pragmatic factor: industrial reliability. The real strength of the Sherman lay in the industrial and manufacturing systems that produced it, which imbued these vehicles with remarkable mechanical dependability, consistent availability, and a straightforward design that simplified maintenance and repair. By mid-1943, German engineers at Kundorf fully grasped this reality, having conducted exhaustive testing and analysis, and they documented their findings meticulously. Their scientific approach involved rigorously repeated tests, which conclusively revealed the American advantages in reliability and operational readiness. However, recognizing a problem and actually solving it are two fundamentally different pursuits. German industry, despite its technological prowess, lacked the capacity to reorient its production lines around the principle of reliability in the midst of a war that was rapidly turning against them on multiple fronts. They were fighting a desperate, resource-stretched conflict against enemies who had demonstrated greater industrial capacity and logistical flexibility. Conversely, American industry had, over decades of civilian automotive manufacturing, integrated reliability and practical, mass production principles into its manufacturing ethos. These principles, developed in the competitive, commercial marketplace, were simply extended into their wartime military production, with remarkable success. The story of war's most telling proof lay embodied in a single tank, referred to as War Daddy II, that had been captured in Tunisia and subjected to months of meticulous, systematic testing at Kumdorf. Despite its unremarkable appearance, just one among 49,000 Sherman tanks produced, this particular vehicle stood as a testament to the profound advantage American engineering had achieved. With every kilometer it traveled without failure, it hammered home the point that German tank design had taken a fundamentally misguided path by prioritizing specifications, such as armor thickness and firepower, at the expense of reliability. Each test, which demonstrated American automotive and engineering excellence, reinforced the idea that industrial maturity and a deep reservoir of practical manufacturing experience mattered far more than theoretical specifications and fancy technical features. The repeated comparisons between Sherman tanks and their German counterparts in terms of reliability showed a consistent pattern. Americans had effectively solved the core problems of durability and operational dependability. In contrast, German engineers had failed to recognize the importance of these issues, often failing to even identify what needed to be solved. The tank itself, while not extraordinary in design or appearance, merely another product of the immense industrial effort, symbolized something far more consequential. It was a stark, irrefutable symbol that Germany had already lost the industrial war, despite ongoing combat. Its failures in reliability underscored the broader reality that American productive capacity had grown so formidable and efficient that the Germans' technological advantage was rendered moot in the face of a reliable, well-produced vehicle. The war was being decided not only by firepower or tactics but by the strength and resilience of their industrial base, an advantage ultimately impossible to overcome once proven through relentless, rigorous testing. No matter how advanced their German technology was or how sharp their tactical strategies might have been, the outcome remained unchanged. The outcome was consistent, unaffected by the level of German technical sophistication or the precision of their tactical maneuvers. Whether their equipment represented the pinnacle of engineering or their military tactics demonstrated exceptional planning, the results did not differ. It was as if these factors held no sway over the final decision. In essence, despite the high caliber of German technological and tactical efforts, they were unable to alter the predetermined outcome, which stayed uniform regardless of their expertise or innovation.